So as I was saying, this chapter is on simple linear regression. Now, regression can get very sophisticated. We're just looking at linear forms, and there are non-linear forms, and all right, so many different ones. No, and it can involve many variables as well. But it's an important technique used in business and economics and many other fields. So it's a good thing to get familiar with it. I wanted to come here and just give me a minute. No? Um, yeah. So as I was trying to convey, linear, you see in most of you have done the economics classes, no? So you know that in economics we say, oh, the law of demand, the law of supply, the law of diminishing returns, all of those laws, right? How were they arrived at those laws? They use these techniques. So if you can imagine, now we say the law of demand, but it wasn't always like that in economics, right? You kind of have the hunch, if you haven't studied regressions and stuff, you have the hunch that, yeah, when prices goes down, obviously I'm going to buy more. If the price goes up, I buy less. And especially if there's substitute items and complementary items, which again we've discussed in economics. But now it's in the principles class, you learn the law of demand. Well, how did they come with the law of demand? It's because initially they had the hunch, but you can't just go with your hunch because your hunch could be wrong, right? So you devise an experiment, and then you either ask people what they would do if the price changed, or depending on how you're going to structure your studies. But in all cases, when economists do it, check if the price goes down, what would be the consumer's behavior, and it will be buying less of the item or buying more of the item if the price goes down. So they use regression to come up with a relationship between price and quantity purchased. And because it's so consistent, that it starts as a hypothesis, as we've done in this class. You started a hypothesis, and then it rises up to whether you call it principle or you call it a law or you call it, it depends on the practice of that particular field. So in economics, when we say if it's been so what do you call it? Is so validated that and no exceptions, then it rises up to where you would refer to as the law of supply or the law of demand, right? And we will see in this chapter that the possible relationships, when you're looking at a linear specification of a regression, the possible relations are always the ones that, again, in principles, we say it's a positive relationship or a negative relationship. Right? It comes in different names, right? Inverse relationship, indirect relationship, like that. But boils down to mathematically, okay, you're looking at what? You gather your sample, you check the relationship between the two variables, and using ordinary least squares to try to compute for that those beta 1, beta 2. In this case, in chapter 15, we'll look at beta 2 and generalize to other as many variables as you wish. But what I wanted to kind of start out with is that's how important the tools are, because in economics we used this technique to try to come up with what are referred to as principles or laws, and then in sociology, in chemistry, and right, it's the same technique. Every time you hear the word scientific method as a way to arrive at principles and laws and theories, then you're at the core, part of the core of that scientific method is going to be included there. Is going to be your regressions, right? And although we're looking at linear here in this course, after this you go to higher level statistics class and you will explore other forms of regression like that are nonlinear, right? Okay, so as we've done in the past classes, we'll go over the PowerPoint, looking at what to get a theoretical understanding, and then we'll do some exercises. Now for this and next chapter, you really want to start using more and more just the software to compute and then make the interpretation on those statistics rather than doing the manual, right? The text in the exercises, they will still involve some kind of manual computation. And even though sometimes it asks for, you could use the manual computation, and I see the videos, they use manual computation. If you know where to do it automatically, then you can just skip to the use a function to run your sample estimates, and then make interpretation, and then put the correct answers into the homework, and then it would work. No, so we'll do some of that. The other thing that I wanted to cover is at the end of this. Maybe we'll do at the end of the class. We can do that. At the end of this week's class, you will see at the very bottom, you'll see course evaluation. Every semester, you ask to do this, no? So maybe when there's maybe 15 minutes left, I'll stop, and then, so remind me, we can do that. And you allow the time to do it in class. If I don't allow it, usually very few do it, and then I don't have enough. And then they're going to move the dates back, and then in the end, we don't have that many participation. It doesn't really help when we don't get feedback. No, and this is actually the opportunity to say what you want to say, especially like the class format, as I was asking last time. We're doing NMC has moved toward face-to-face, but maybe maybe it's best if the class was online or virtual, or and maybe only meeting one class, or or if you have suggestions on how the class should proceed, how best to get the materials, then those would really appreciate if you, in addition to making sure the boxes are ticked, that you put in the comments. That would help me out in the next semester. Okay, but we'll give some time for that one, maybe 15 minutes into the end of the class. Okay, so let's go and look at chapter 14, no? So again, simple linear regression. So for this chapter, there's quite a bit of content to cover. So we look at the model, simple linear regression model, and then we look at the least squares method. This is the method that is, we will see that it's really similar to what we've looked at before, right? You're still looking at computing the total variance, and then you're going to see how much of the variance is due to your independent variable. And then in this case, we're only going to have one independent variable, then the residual is going to be your error, no? But the method that is used in this context is what is referred to as ordinary least squares, no? And then we'll look at what is a coefficient of determination. And then we'll look at the assumptions of the model. Those are important, because if the assumptions of the model are violated, then it means several things. It could mean that the linear relationship is not an appropriate one for the problem that you're working with. So you got to look at for alternative methods. Maybe it's a quadratic, or maybe it's a logarithmic, or whatever. And then, so we look at those assumptions and see how we test for for the validity of the assumptions. And then do test for significance. But these ones we're familiar with now. We've been using, well, now we know all of the different test statistics, no? The Z, the T, the F, the chi-square, and so on. And we know how to run the test, right? Set up the null and the alternative, and then you do use the p-value or the critical value or the confidence interval as your ways to reject or to assess whether to reject or not reject the null. So all of those they're going to show up again in the context of a simple linear regression. And then why the linear regression is a good model is that it then, once you've estimated your equation, you can then use that equation to come up with estimates given the new values for that independent variable, or you can make predictions. No, regression is used a lot in the context of prediction. No? And then we look at computer solutions. So again, this confirms what I've been saying all along, and that eventually, once you move on to real work, you don't really do the detailed computation. The software does it for you, and you're doing mostly the most important thing would be, okay, given a problem situation, what among the techniques that we've covered, which one is appropriate for the problem you're working with? And then use a computer software to solve. And then when the output is printed for you, how do you make the appropriate interpretation and conclusion to what the results of the study is? And then, so we look at these the assumptions. These are so to check for the model assumptions. We use the residual analysis, right? And then the residual analysis can also be used to check for outliers, right? We already know what outliers are from the previous chapter, but we'll look at it in the context of regression models or regression analysis. And then some practical advice on big data and hypothesis testing in a simple linear regression. No. Okay, so let's see. So for the objectives, and there's quite a few of them also, develop an equation that estimates how two variables are related based on a sample data. And then obviously we're looking at regression equation in this case. Use a simple linear regression equation to predict the value of the dependent variable given. So once you've come up with your estimated equation, how do you use it to predict or estimate values or predict new values for the dependent variable? No? Provide an interpretation of the intercept and the slope of an estimated simple linear regression. So these are your beta null, beta 1, and then next chapter, beta 2, 3, however many independent variables you're working with. Then compute and interpret the coefficient of determination. So we will look at that. That's your R square. And then compute and interpret the sample correlation coefficient. We already saw this before, right? In chapter, right, I can't remember, one of the chapters talk about correlation. So it turns out that if you took the square root of this guy, you get your correlation coefficient, right? Which tells you if there's a linear relationship between the two. We already know from the previous chapter, a relationship could be what, a positive one or a negative one, or if there's no relationship, the coefficient is 0 or close to 0. No? Okay, then use the t-test. So we already know how to use the t-test. We'll use it in the context of a simple linear regression. And then use the f-test. We already know that. Calculate your ANOVA tables. But in this case, most of the problems in the homework, you can quickly get your ANOVA tables, your T, your F, by just running rather than manually computing them. You can just use Excel stat or use the functions in your data toolpack. No. Develop a confidence interval for the mean value of the dependent variable y given the value of x. And then develop a prediction interval for individual values for the dependent variable given the value of the independent variable. And these are very time consuming to compute. So again, once you understand what they are better, you just use the software to do, and we'll do it in this chapter. Use the residual plot to assess whether the assumptions of simple linear regressions are valid, right? And then use residual analysis to identify outliers and influential observations. No. Okay, so let's look at get introduced to the material. So in many cases, your managerial decisions often are based on relationships between two or more variables. No. So we started out by me saying that if you know the relationship between your price and quantity, and furthermore, you know not only that the law of demand says reduce the price and quantity purchase goes up, if you go further and use this technique to estimate your elasticity, then that elasticity will further tell you that if your elasticity is greater than 1, by decreasing the price, your total revenue will increase. Yeah. And then if the elasticity is less than 1, you decrease the price, the increase in revenue is going to be, instead of increasing the revenue will decrease. No. So I'm bringing those up to try to make sense of what the significance of estimating those relationships between variables, and I'm using price and quantity in this case. Statistical procedures called regression analysis can be used to develop equations showing how variables are related. Again, in this case, we're confining the type of relationship to a linear form. The variables being predicted is called, so these are the good terms, no, dependent variable, and conventionally denoted by y. So the practice here is the same practice that if you were in the math class and talk about these same concepts, independent variable, dependent variable, and it's the same that you've learned there. By convention, your independent variable is on your vertical axis and your independent is on your x-axis, no? So the variables being used to predict the value of the dependent variable, or sometimes predict, or sometimes use the term explanatory variable is also another term that is used for independent variables. That is, the independent variable helps explain for, right, variations in the dependent variable. Okay, and usually denoted by x. In this chapter, we consider simple linear regression, right? The simplest type of regression. And you can have multiple linear regression, and then it gets sophisticated into nonlinear forms of regression. No? It involves one independent variable and one dependent variable, and the relationship between the two variables is approximated by a straight line. Here's the linear, right? And regression analysis involves two or more independent variable. That would be called multiple regression, which is the topic covered in chapter 15. No. Okay, so the model. So how does the model look like? So here's the specification of this model. No? The regression model is the equation that describes how the dependent y is related to your independent x with the error term. That error term is a significant one. No. Now the simple linear regression model is described by this. So here's your dependent variable, and this is your intercept, and it'll be, yeah, so they're being defined here, no? Your beta 0 and beta 1, these are referred to as the parameters of the model, and that's your intercept, that's your coefficient that define the relationships between x and y. X in this case is independent, Y is the dependent variable, and then here's your error term, no? Error term. That error term accounts for the variability in Y that cannot be explained by the linear relationship, right? So we will see later, we're going to use the same technique that we're going to use that we've used before. We're going to use the ANOVA and to help us determine what that error term is going to look like. The simple linear regression equation, so from the model, move to the equation form, you drop that error term. When you're solving for the equation, you're going to be solving for three unknowns, no? So you're going to be solving for beta 0, beta 1, and the error term. So once you've known the two, the third one would be predetermined, yes? So when you collect your data and actually do your computation, you need not spend your time trying to compute for that third value because it'll fall out as a residual, no? Okay, so and the definitions are important here in the notations. Sometimes those are what throws us off at the beginning. So the expected, where Y is the expected value of the distribution of the Y values for a given X value. So remember, we're eventually we will estimate and try to predict the Y value given a particular X value, no? So because there's an error term there, the prediction or trying to explain the variability in Y that is due to X is going to end up with some kind of error there because we're sampling to come up with that estimate. Yes. Okay, that'll come clear later. So the beta null is the intercept, as I said before, of the regression line, and then your beta 1 is the slope of the regression line, and its sign dictates the type of linear relationship. So we started out by saying the relationships could be a positive one and a negative one, or there's no relationship. And so these are the familiar lines that I said the law of supply is a positive relationship between the price and the quantity demanded, yes. And then the law of demand says the negative relationship between the price and the quantity. You see, I'm trying to run the parallel between the relationship between this class and other classes, no? And then if the beta 1 is 0, it means that there's no relationship between the two, right? In many cases, many variables are not related at all, no? Okay, so the process, this is a good model for the process. The estimated simple linear regression equation is, as we said, so you're going to be estimating a line, right, that plots the Y values that minimize the variance between that line and the individual observed value of the Y. That's what we're doing. So Y hat is going to be equal to beta null and beta 1 X. The graph of the estimated simple linear regression equation is called the estimated regression line. And then your estimated Y is a point estimate of expected value of Y for a given X, and beta 1 is the intercept and beta 2 is the slope. So to this model encapsulate what we've tried to describe so far. So your model specification for a linear model is going to be takes that form. And then to estimate that model, you're going to use the equation, and that equation is going to take this form. Yes. And then what you're interested in is what? You want to know the population parameters, right? But we know that's difficult to get all the population data that would give us those population parameters. So we're sampling, no? So when we're sampling, our sample statistics are the statistics we come up with are going to be based on a sample, and those samples are going to be the estimated values for that beta 1 and beta null, no? So once you get the specification, this process is the same if you're using a multiple regression or you're using a non-linear equation. You have to specify the model correctly. There has to be some theoretical reasoning why you would choose that to begin with. And then you collect the sample data and then fit the data into the model and then run ordinary least squares against the data and then estimate your betas and then come up with your appropriate interpretation. Is there a relationship? Is the relationship positive one? Is it a negative one? Or if the relationship doesn't exist, then that would be your conclusion, no? Okay, so the least squares method, as we said at the beginning, is the procedure that you use to, or method that you use to estimate your coefficients, your beta 1 and beta null. It uses the sample data to provide the values of your beta 1 and beta 0. It minimizes the sum of the squares of the deviation between the observed value and the dependent variable and the predicted value of the dependent variable. So notice this, right? You're minimizing the deviations, yeah? And that deviation turns out that's the error, right? That's the error between the estimated and the observed value. So these notations are really giving us that. No? So y I is each of the observed value of y, the dependent variable, and then the y hat is the estimated value, right? Based on your simple linear equation, no? And you square that difference, and then you sum, and that's the process of you're trying to minimize that sum squares of deviations between the observed and the dependent variable, no? So the slope and the y-intercept. So the slope, beta 1, right? And the y-intercept, beta null, right? For the estimated regression, the equations for them are these ones, no? So hopefully now it's, once you see it, it's quick to make the interpretation, no? You have to first come up with a mean of x, and then take the difference of each of the observed value of x from the mean. Then you do the same thing for y, and then you multiply the corresponding difference for x and y. Sum that, and that's going to be your numerator. And then in the denominator, you take the difference of the observed value of x to the mean of x, square those values, sum them, and that's going to be the denominator, and that's going to give you your estimate for your beta 1. Once you get that, I only have two equations. So once I have that, I can then, or two unknowns in this case. So once I have that, I plug that back into the equation, and then I solve for the intercept or the beta null in this case, no? So okay, so let's take on the example, right? So that's the theoretical understanding that we need to have, right? And then to get solidified in our understanding of what that simple linear equation does is to look at a specific example, no? So here, the specific example is one that involves a pizza parlor, no? So this pizza parlor is located in many different cities, and the pizza parlor happens to be next to maybe colleges or universities, no? Those of you who've been in big schools, I went to Arizona State. And at the time I was there was about 45,000 students. So the whole around the campus is just businesses catering to that population age from 18 to 25 or something like that, right? So lots of pizza parlors, lots of fast food stuff, mm, bars and stuff and things of that nature. So and it's big money to serve that population as well. So uh, Armand's Pizza Parlor, a chain of Italian food restaurants located near college campuses, believe that the restaurant's quarterly sales denoted by Y, so Y is sales is the dependent variable, are positively related to the size of the student population, right? And that population is denoted by X, no? So if we use the sample of 10 randomly selected restaurants to build a scattergram depicting, okay, so we've used the scattergram before in the previous chapter to check for, visually check, no? So in the first 2 or 3 chapters, we said that when you're trying to understand if there's a relationship between two variables, one of the first things you can do is you can plot the values, no, and see if there's appears to be a relationship. So if we let me pull this over to the side, and then if you and pull the value, pull the data file for Armand's Pizza, so we can, as we go, demonstrate how to eventually come up with your regression equation, no? So if we, you can get the file, download the file from the 2 places. You can get it from the textbook, or if you went to the data files, chapter 14 data files, and open that one, you will see that one of the Excel files there is Armand's, no, that one. So if you're wanting to play around, yeah, you can certainly do that. Let me just chapter 14. And then I'll say CL, CW. All right. And then save it. And then open it, no? Open that. I don't want the plus anymore. Okay. So there's the data file, no? Can you see it? So if you have the data files, let me move this over to the right. So notice that the restaurant is just your primary key to identify each of the restaurant uniquely for the 10 restaurant. And then you have the population and then the sales, but these numbers are scaled, no? They're in thousands, no? They're in thousands. Okay, so if I switch back to, let me see, oops, no, yeah, this one. I want this one. Okay, there. So if I want to replicate the, sorry, it gets smaller, no? If I want to replicate the scattergram or scatter plot, then let me increase this so we can see it easily. You do what? We already did this before. You go to insert, and then you're gonna look at the charts, no? And then you're gonna say, okay, there's different. So I'm gonna use this one. Oops. Better I select the. See how it's going to give me the. Yeah, there you go. Select the data set first, so that it, when you're plotting, it knows to, right? So you select the scatter plot, and then it's always a good idea. Usually when I'm doing stuff, I get lazy and I don't, in the interest of time, I don't customize the charts, but it's good to, whoops. it's good to customize them. So this may be what Armand's, maybe estimating or predicting Armand's sales, maybe like something like that. Then also you can put your axis titles there, horizontal. Oops. These are what? These are population, correct? Student. Ah, this is why I don't always do it, is because it can take time. But I just want to demonstrate. And then over here, I can do what? Title for the vertical. And that would be what? Sales. And that's in 1000, no? So it's always a good idea to do that. Something like that. And then while we're here, we can already, because the tools are pretty good now, you can already come up with your equation, right? Estimated equation. So to do that, you can go here. There's different ways. You can go here or go here, and then just find where. So plot a line. So that's how quickly you see it, right? But what's the process that plotted the line? It was the ordinary least square method that we referred to, no? That plots the line that minimizes the variance between the individual y values and estimated values of y, you see? So, okay, if I went here one more time and I said plot the trend line, so I plot the trend line, and then if I want my equations there, I can go further and say more. And then some of the options here are going to be, let's see. Oops, I got the wrong one there. It's going to say display the equation on the chart. So I display it. And then it says display your R square. So R square is coefficient of determination, no? So if I already, so pretty much just from the chart, and Excel anticipates this, so it builds them into your charts, no? So if you knew your data set already and you're pretty confident, or after you've gone through the testing procedure that we will walk through later, and eventually have to publish your results, then this would be one way of, right, publishing your results, no? Depending on the nature of your, right, who your audience is, this might be already a good one, no? So if the reason why I wanted to show that is that so that when we go back to the PowerPoint and try to go over the description of these things, we have that already. We're aware that it's actually the computations now is pretty straightforward, right? As long as you've done it, so you know what you're trying to do. So in this case, we know how that plot was created, no? Now, because this is an intro class, we go through that sort of boarding steps of how those beta 1 and beta 0 are computed, right? So here's those equations, no? So the calculations necessary to develop the least squares estimates, estimated regression equation for a sample of 10, and the data is already given. So, okay, so the estimate your beta 1, again, this is the equation that we saw before, right? Derive the mean, and then take the difference between each of the x observations from each mean. Same thing with the y, and then multiply the corresponding values for differences in x and differences in y's. and then sum them all up. That's the numerator, and then the denominator is, again, perhaps shouldn't, in the interest of time, I won't repeat that, no? Then, so that becomes your, right? And then once you have your beta 1, you substitute it back to your um, uh, beta, to solve for beta 0, you substitute it back to the equation and then solve, no? So that's the estimated regression equation for Armand's Pizza Parlor is this one, which again, I said, once you know what ordinality least squares does, then you can come here and just plot and throw your equation already on your chart. And if you're describing this to somebody who knows what ordinality least squares is, then they don't need to see the detailed computation. They trust that you've done your work, right? So, okay. So I won't, in the interest of time, I won't go through all of these, right? You should already just read them by just looking at the equations on the top of the column and look that, right? Okay, so again, I will, okay, well, let's look at the interpretation. So the slope of the estimated regression equation, beta 1, which is 5, is and not the sign of the coefficient is positive. So it implies that the student population has a positive relationship with the sales, no? So as the student population increases, then you expect the sales to also increase as well, right? In how much so is based on that equation that we've estimated, no? This equation that we've estimated. And so it's it says what? If it's 5, it means that what you're $5 per student, right? Increase in sales by $5 per student. So we can also use the estimated regression equation to predict the value of y for a given value of x. For a restaurant located near 16,000 people for an hour, we just do what? We substitute the values. In this case, we're working in thousands, right? So notice it's 16,000, but I'm putting 16 here only. And then, but in the end, you ought to be sure to multiply everything by 1,000 to get back to your true unit of measure, no? Hence, we predict the quarry sales of 140,000 for this restaurant again by substituting. So that's how it's so. This technique is very, very important, right? Because you can gather your historical data and then decide if you're trying to build another pizza parlor. Should you build another pizza parlor, or should you locate another pizza parlor next to another town? Then knowing what the population of the college or the university is will help you make the determination whether you should pop up a new parlor or not, no? Okay. Now, we turn our attention to that residual, no? And at this stage, good to remember what the notations are for that residual is, no? So that residual is what? That residual is, so the estimated, the observed value subtracted by the estimated value, no? For each of the ith observation, no? That is the difference between the observed value and the dependent variable yi and the predicted value of the dependent variable, no? So the sum of the squares of the residual is also known as the sum of squares due to error, no? Is the quantity minimized by the least squares method, no? So that residual is, in this case, synonymous to that error, you see. Okay, so, and that's the equation, no? That's the equation to come up with that sum of squares error. And how do we compute that manually? So again, I'll just point to it, no? And eventually we will do some examples where we would just use Excel stat to compute the statistics, no? And make the interpretation. But again, you will go through, subtract the differences and then, square them. And then once you square them, sum them, and then you'll get your sum square. And it's the same process that we did in the previous chapter as well. No? Sum square error. We calculated them in the previous chapter. And then also the total sums of squares. Again, we've done this in the previous chapter. So now we're doing it in the context of ordinary least squares. So the ith restaurant sample, the difference between the observed y and the now this is the average of y, provide a measure of the errors when using y to predict the sales, the average to predict the sales. The corresponding sum of squares called the total sum of squares is denoted by SST. So again, the difference here is I'm subtracting the observed value from the average and then summing those differences. No. The table to the right shows the calculations. Okay, and then the value here, right? And now note how much the larger the squared deviations of the SST are when compared to the squared errors of the SSE. And this diagram helps us to see what the differences are. No, so the difference of the estimated value, or rather the predicted value, the difference between that and your mean provides a measure of how much that y hat on the estimated regression line deviate from your, right? So here's your y hat, and then here's your, this is your average of the y, and this is your y hat, no? Okay, so hopefully when you see these, it's familiar from the previous chapter, right? We're just using in a different procedure. So the total sum of squares can be partitioned into two components. The sum of squares due to the regression. In the previous chapter, we said sum of squares due to treatment. Now we're saying sum of squares due to the regression. So it's SSR. And then the sum of squares due to error. That's the same one we defined before. So that is your sum of squares total can be partitioned into, that is your total variance could be the split into the variance that is due to regression and the variance that is due to error. No, that's what we're saying here. Okay, and then you substitute the values into it. You can, because we already know the total sum of squares, we know we've computed the error due to, the sum of squares due to error. Take the difference and you get your sum of squares due to regression, or the other way around. You can do, if you compute for your SSR and then your SST, then your SSE is computed by just taking the difference. No. Okay, and so now what is the coefficient of determination? So estimated regression equation provides a perfect fit when every value of the dependent variable y lies on the estimated regression line, so that your difference is zero, right? Your error is zero. What we're saying, let's see, there's a chart here that helps explain. What we're saying is that the lines will be, the estimated line and the observed value are going to be right on top of each other, is what we're saying here. And because your SST is split into SSR and SSE for perfect fit, the SSR equals SST, and the ratio, they must equal to 1, no? So the ratio of the sum of squares due to regression to the total sum of squares, that's what we refer to as the coefficient of determination, and that's denoted by your R square, and it's a what? It's the measure of fit, how well the line fits the observed value of y, no? So the coefficient of determination can only assume a values between 0 and 1, right? And it's used to evaluate the goodness of fit for the regressed, for the estimated regression equation. No? So in this case, if you plot it, substitute the values and solve for it. So if your possible values are between 0 and 1, and your R square is 0.9, and it's pretty close to 1, no? So that means the fit, it's a good fit, in other words, no? And so thus about 90% of the variability in the quarterly sales of Armand's parlor can be explained by the linear relationships between population of students and quarterly sales, no? So in this case, you'll be confident. We still have to go through and test the validity of the equation. But if, and we will test that it's valid. So when it's valid, then the estimated equation is a good fit to use to then estimate the values of sales given an X population, student population, or predict sales given student population. No. Okay, so we got the determination of what was it? Coefficient of determination, and then the correlation coefficient. Again, we already know this, and to derive this in the context of ordinary least squares, you just take the what? You just take the square root of R square and then check for the sign. No, if the sign is negative, the relationship is correlation is a -1, it's a positive then, right? So in this case, take the square root of 0.907, and then you'll get your correlation coefficient at 0.995. No, so again, very hard, very strong positive linear relationship between X and Y in this case, because the values of the, what are the possible values of the correlation? It could be -1, between -1 and +1. So if it's close to 0, then there's no correlation. If it's closer to -1, then it's a strong negative. It's closer to +1, then it's a strong positive. No. Let's see. Wonder if I want to go into the. Let's leave the assumptions for the error term for next time we meet. Okay, I think instead let's go to the homework maybe, and do a 1 or 2 of the homework there, so that we'll do the rest of the stuff and give you time to read the materials, and then do the rest of the stuff when we get back on Thursday, and then give us some time to do the course evaluation. No? So if we went to let's go to there, no, and let's do an example. I mean, let's do one of the homework so it makes sense. And I will post the worksheet as well. But you will see that most of the time, it's just knowing which routine to run and then making the interpretation is really what's necessary. When you're making your interpretation, if you feel like you have to go back to the text, that's really what you want to do, is go back and forth until you get very solid in your understanding. And then eventually you repeat, and eventually the repetition is no longer necessary because you already know how things are. No. Okay, so let's go to 14.2 and look at maybe the first one. No. So the first one is let's see. Let's open that. And it gives you estimated minutes. It's probably because if you're doing manually, that's going to happen. So you're given our 5 observations for X and Y here, and then you're going to, the question is, How does the scattergram developed in A indicate about, okay, so first one is develop a scattergram for these data. And then second one is a interpretation one of that. And then the third one is develop the estimated regression equation, computing the values of, right? And then come up with use the estimate to use the equation to predict the value when x is equal to 2, right? So if I have this data here, let's we got to clip the data first, right? So I'm going to clip the data. No, I'm going to copy the data. I'm going to go to Excel. And then I'm going to, where are we? I'm going to, I'll just use the same one, worksheet, and just get a workbook and get a new worksheet. So I'll paste the values there. I think everybody knows how this works now. You paste the value, but in Excel, you want to pivot so that your data are in column. So I'm going to copy this, and then I'm going to paste transpose. And then I will get rid of these on the top because I don't need them anymore. And what I usually do is I prefer to have my labels right on top of my data points. And so I do it this way, no? Now, so now you can decide how best to attack this problem. You can do this by just using the scatter plot, correct? As we demonstrated earlier, no? So I can just select these and then I go where? Insert. And then I'm going to look for this one, right? And then I select the scatter plot, right? In the interest of time, I won't customize the chart. And then now I can already answer some of the questions, but better if I put in more information so that I can answer the rest of the question when I'm given the rest of the question. I could put in my equations now. You know that you can do your equations right here in the scatter plot by just going to more and then tick the box for display the equation and display the coefficient of determination, or otherwise known as the R square, no? Okay, so we got those. And then let's see, maybe we have enough to answer the question. So let me move this over here, right? Let's save this guy and then let's go here. So now can we determine, let me move this over here. Oops. Can we determine what the chart is going to look like? Which one is it? Yeah. So there's a couple that are kind of close, so you got to make sure that, right, the values are. So notice that scale, notice the scale before you make the choice of which one. You know? So obviously you know that the choice is going to be where the scale matches, no? So that's the one, this one is. And then what's the other question? The other question was, what does the scatter diagram develop in A indicate about the relationship, no? So obviously we see that it's what? It's a positive one, no? It's a positive one. So that is as the population or not, whatever this x-axis, whatever is measured in the x-axis increases, then your y increases as well. So the relationship appears to be a positive, and it's a linear one, right? We're only working with linear relationships, so it's a linear relationship. So we select that. And then what are the other questions? The other questions is, or rather, it says develop the estimated regression equation by computing the values of beta null and beta 1 using these equations. But as I said, you really need not do that, right? Because you already see the equation here. So you can just drop that equation here. Just make sure that you know that Excel kind of switched the order, right, and puts the intercept term after. So that's it's just the formatting difference, no? So you can see that your intercept or beta 0 is 1.4. So, and then the preferred format would be specify or state your beta null first, and then your beta 1, and then your x, no? So in this case, the equation is already there. You just reconfigure it and then put it there, and you're fine, no? But then it says, use the estimated regression equation to predict the value of y when x is 2. So now how would I do this? Okay, so now I have to construct my formulas that would use the equation to predict, no? So I could come here and say what? I could say y here, and then let's see, y equals 2, just kind of, right? And then your beta 1, oops, I should space, right? So I try to, and then beta null, right? And then beta 1, right? And then x, no? And then now I just, so my x in this case that he wants to is, x is going to be what? 2, yes. Beta null is going to be what? I mean, beta 1 is going to be what? 2.2, makes sense? And then my intercept is going to be what? 1.4, makes sense? And now I solve on the other side. I'm just going to solve, right? So this is going to be what? Equal to what? Equal to D26, yeah? Add that to what? Add that to the product of your beta 1 times what? Your x value, right? And then enter, and you get your, let me do this. If I, oops. If I kind of clean things up here a little bit, it would look more better, no? If I do this, no? And then put this in the middle, maybe, just to make it look, prettier, no? And now you have it, no? So just that, give me a little bit of time. I have a class at 6:30. Okay, so you get, yeah? So hopefully, so that's for problem 1 for homework 2, no? So I'll put this up on the, I'll put the recording up on the this week's Moodle page. So if you need to, you can look at it. But hopefully by just observing, you now see that most of the example of the homework that are done here, no need for us to go and compute manually, no? Just either use the scatter plot, if necessary, use Excel stat to do the rest. If it's asking for ANOVA, instead of, for example, let me just use a few minutes. I want to leave 15 minutes to do the evaluation. So for example, if the question asks for ANOVA, right, then I would do this. If this is, I'm just pretending that this is the data set that is for ANOVA, then there are 2 ways you can do this. You can go to data and go to data analysis, and then find regression here, and then run it, and just specify where the data is. So for y, make sure you select the correct vector for y, and make sure you select the correct vector or column for x, no? And then you tell it, okay, I'm using labels. If you're going to do a confidence interval and test, you're going to specify those. And then, okay, let's put an output here also. And then let's see, if when you go to homework 3, 4, 5, it's going to ask for more statistics. Like it's going to ask for what is the residuals, what is the standard residuals, give me the plots that you can then use to populate your answers on the other side. No? So kind of stepping ahead over here. And let's see, if I put the output here, for example, and then click OK, then now you see here's your ANOVA, here's your regression coefficient, this is your coefficients, you see, and then here's your residual output and so on. No, so now it's a matter of making the interpretation. So here's your, remember, your regression, and this is your residual is your error, right? And then the regression for your SSR is that, and this is the SSE. No, now the other option would be this: if you're given the same problem and it asks for more statistics, one of the best ways is to use the Excel stat. So let me just demonstrate that while we're here in the next few minutes, so that when you're working with your homework, that's what you want to do, is just get the data and then plug into the right routine and do it. Your linear regression is going to be under model and predicting, no? And then if you select that one, what you need to do is again, similarly, you got to tell it where's the dependent variable. So this is my dependent variable. Where's my explanatory variable? So different term here, no? Instead of independent variable, explanatory variable. And then you specify where that is. And then you go to options and, okay, that's stay the same. Prediction. We'll talk about prediction later, but for now, I'm just demonstrating how you would solve most of the problems, right? If you go to output, okay, you can specify these, right? And then go to chart, and now the rest of it is, if you click OK, it will, and we're already familiar with this from the previous use of Excel stat, no? And so here's your summary statistics. Here's your correlation metrics, right? So again, you don't need to compute those because if you're using the right tool. Here's your R square, and here's your mean square error, and here's your root of the mean square error if you need them. And then if you go down here, you will see, okay, here's your analysis of variance. And now, hopefully now everybody's familiar with these. And then here's your betas, right? So here's your standard error. Here's your t-values, right? And then here's your probability associated with that for when you reject or not reject them also. And then here's your predicted values and your estimated values that are already computed for you. Now, the rest of it is, so where are the answers coming from? Which ones are the answers coming from? I'm just showing you how you can quickly come up with those statistics. Next time we meet, we'll go in there and solve another problem and then point it out. So, but those of you who are kind of ahead and wanting to go before what we've covered so far, you can do that, no? You can already do some of the homework up to part 6 already, you know? Okay.